The mathematics of simple harmonic motion are similar to the mathematics of circular motion, in the same way that circular motion mathematics are similar to linear motion mathematics. Linear motion is limited to 3 dimensions travelled, so we define start and end points. Circular motion is limited to 2 dimensions, so we limit linear motion to within a circle. Simple harmonic motion is limited to just 1 dimension, so we limit the equations of circular motion to a line. As we've described, you can show simple harmonic motion as the motion of a spinning object seen from the side only. This is what we do with the mathematics of simple harmonic motion. We take circular motion and look at it from the side. In a circle, you can define the point along either one plane or another plane perpendicular to it by using right-angled triangles. Imagine a circle containing 2 radii. One radius is fixed at the horizontal, the other is only fixed at one end, the end at the centre of the circle. The other end is free to move about the circle. Moving this radius around the circle, you can draw right-angled triangles by dropping a line straight back down to the other radius at the horizontal. The right-angled triangle is made from the line you drop down to the horizontal, the opposite length, as it is opposite the angle from the centre of the circle. The horizontal line from the point the drop-down line meets the horizontal radius and the centre of the circle, the adjacent length, and the moving radius that joins these 2 lines together, the hypotenuse. The horizontal length is given by SOHCAHTOA. See AS Physics podcasts on linear motion equations, as x equals h cos theta, where h is the hypotenuse. From circular motion, we know that theta is equal to the angular speed times the time. The faster an object spins in a fixed time, the greater the angle it will cover. So we have an equation to cover the distance an object moves in one plane around a circle. X, the displacement an object is away from the start, or equilibrium position in our case, is equal to the hypotenuse of the right-angled triangle formed as above by the cosine function of angular speed times time. The terms for a simple harmonic oscillator aren't the same as the terms for a spinning object. The oscillator doesn't have an angular speed or a hypotenuse or any angles, so we need to explain how to apply this equation to an oscillator. The hypotenuse is the longest length in our right-angled triangle. It is the same as the maximum displacement of our oscillator from the equilibrium position. We give this a symbol A for amplitude. The angular speed can be expressed as the frequency of rotation of an object multiplied by the circumference of the circle, that is to say 2 pi f. Our angle now becomes 2 pi ft, where f is the frequency of oscillation of the oscillator rather than the frequency of rotation of our plate. T is the time point you wish to know the displacement of. So, our first simple harmonic oscillator equation gives us the displacement of our oscillator from the equilibrium position as the maximum displacement of the oscillator, A, times the cosine function of the frequency of the oscillator multiplied by 2 pi and the time you assign. X equals A cos 2 pi ft. You can think of this equation as telling you where between the maximum positive displacement and maximum negative displacement your oscillator is at a given time that you choose. Velocity is displacement divided by time, so you can simply divide the displacement above by time. We already know that velocity follows a negative sign function, so we could give velocity like we did above as a value compared to the maximum velocity of the oscillator. Negative a 2 pi f times cos 2 pi ft. We also know the acceleration follows a negative cosine function, which would give it as negative a 2 pi f squared times cosine 2 pi ft. In mathematics there are concepts called identities. In trigonometry, where we use sine, cosine, etc., we can use these identities in place of some trig functions. So for velocity, we had an equation which gave us a velocity as negative 2 pi times cos 2 pi ft. The 2 pi is inside the trig function and also outside. We can simplify this equation using the trig identities and surds to be plus or minus 2 pi f squared root of a squared minus x squared. Getting displacement to 0, x equals 0, we know that the fastest velocity is given by 2 pi fa. Our equation for acceleration from above has the equation for displacement within it as well. This means that we can express acceleration in simple harmonic motion as negative 2 pi f squared times displacement. This is the definition of simple harmonic motion. The acceleration of a simple harmonic oscillator is proportional to the displacement from the equilibrium position, but acts in the opposite direction. A simple harmonic oscillator has a force that increases with displacement from equilibrium to return the object to that equilibrium. The further away an object is from equilibrium, the harder the oscillator will try to return to that equilibrium. We also know that the maximum acceleration happens at maximum displacement, but in an opposite direction. So, for our equation of acceleration, we simply give x the value of -1 maximum displacement to get our maximum acceleration value of 2 pi f squared